and greetings for everyone from Finland. So 20 years actually next month. I've been working at 20 years exactly with the arc protection systems globally, and practically every possible industrial sites, power plants, every possible fuel, everything from nuclear to wind and from offshore to land, and with different technologies and different manufacturers. But so this is something 20 years ago, this technology was very new, and nobody had a clue about it, that this kind of technology even exists. So during the years, of course, I have seen a lot of different arc plus incidents has been participating in different investigations, and I have also seen a very nice and good stories that where this technology works and the people can go home safe. So that keeps driving, and that keeps also very good motivation level to tell these stories, and of course seeing a lot of in new countries and traveling to different sites and cultures. It's also a very nice thing. So I will introduce you. I hope this works. First, purpose and objectives of this webinar. I would like you to understand three different methods, different solutions, which are arc detection, arc protection, and last but not least, the arc mitigation. So different three kind of steps. What are the approaches on site, on any installation, any almost we could say that any voltage levels as well, that how to do the proper detection, proper protection, and the mitigation, and what are the differences. I would like you to learn also the different technologies, what is existing, what is available. And after the webinar, I would like people and you to observe wherever you are working. There are definitely some things which can be made safer. Utilize what you know, what you learn, utilize it. Take responsibility of the safety, for the safety, and also share the knowledge, what you learn. And it's very important topic, everything today. And if you know, and if you know people who don't know, you can share the knowledge and tell this story forward. A few things of the phenomenon. First, there are probably someone who didn't see the first presentations, but causes of an arc flash are human errors very often. Everyone probably knows some human error which has caused flash or short circuit or similar, and some people may know many. Obviously, because of my job, I have seen a lot. I have a lot of examples. I can tell one human error example. For example, this happened in nuclear plant, and there was a electrician with a torque wrench, and he had a kind of extension part for the torque wrench, and he was doing the tightening for the L1, L2, L3, all three phases, and the bus bars on top of the circuit breaker, on top of the main circuit breaker. And finally, he had to also do the torque tightening of the bolts for the neutral. And he had to remove the torque wrench extension part and just did it with the shorter torque wrench, the neutral one, and he put the torque wrench extension, let's say, to the wrong place. And he forgot it, but it was somehow in the safe area that it was not on the top of the bus bars. And then there was a commissioning engineers are doing resistance insulation level testings and all the other commissionings, which were fine. But when they started the first thing, when they closed the breaker first time and the transformer was live, then the extension part dropped on top of the 3 bus bars. And it was equipped with the one brand arc protection system, and you can still use the tool. So it's one example of the human errors, but there are hundreds, probably thousands stories of the different human errors. Open CT circuits, wrongly done cable terminations. Cable terminations today are done faster and faster and faster, and there are different companies, different type of project handling, a lack of knowledge. It's more business making money and just quickly done cable terminations, and that is one place where arc flash actually may start very easily. Equipment failures, CTs, VTs, circuit breakers, lack of maintenance, also same things. Circuit breaker should be maintained like a certain interval. Loose connections everywhere. For example, unbalance can be easily seen in a phase 1 typically. Phase 1 can be 110%, and phase 2 and phase 3 can be 90% of the energy delivered. Cable faults, dirt contamination, liquids. For example, arc flash, what happened in the coal-fired plant, all the coppers and all the circuit breakers were full of coal dust. And coal dust is explosive. When you do switching, you can count 1 + 1 and you can estimate what will happen, because it will happen. Animals, foreign objects in the gear, like the tool, and then rats. Wherever there is a power plant, there is a cooling water. Wherever there is a cooling water, there is rats. And that is only one animal which can cause. But there are a lot of these examples. How it looks before and after. Of course, the right side picture is something we like to avoid and keep the availability of the plant or the process running. Availability is the number one thing. If your plant is 90% available, it's not a good plant, how it's seen in a business-wise. 99% plant is a good plant. And then of course the safety for people is also, and it must be the number one thing. But in nowadays a busy world, also the process losing has been taken a big part of it. But of course, always the human safety and safety of people should be number one. Then the 3 steps, the 3 solutions, 3 applications mentioned before. The first thing is to detect. And there are different ways to detect arc flash. One of them is current. It's the current threshold, inrush current or current threshold during the arc flash. So this is one way to detect. It's not the only way, but it's a part of the detection. And arc flash detection can be made several ways. One thing how it's done is to use light only criteria. So we just monitor the optical light from the flash and then trip the breaker during the flash. That is done very quickly. It happens in microseconds. Then monitoring the current, it also happens very quickly, typically under less than 1 millisecond, because the current monitoring in practically all of the arc flash protection relays available it has been built differently than in typical protection relays. So it's not the sampled value, it is something different. But current is one of the criteria. For the detection, we also need to monitor light from the flash. It can be done with the point sensors. It can be done with the fiber optics. It can be done in a different sensitivity levels. Or it can be done also with the pressure. And this pressure is something, if you think about the arc flash phenomenon, the light actually, that is the first thing what happens. When the arc flash occurs, there will be a flash first. Then there can be some decrease of the pressure for very short time before the explosion actually starts. And the delay of the pressure is typically seen to be about 6 to 7 milliseconds before peak value. But it is one way to do it also, to monitor the pressure inside the panel. And the sensors for the pressure are quick, are fast, but the actual phenomenon for the pressure is slow. And yeah, for the detection, we need or we can have light, pressure, current. There can be also some other relay types or relay or monitoring types, like for example, voltage drop can be monitored. But the de facto standard, what has been seen now in recent 20 years, has been current and light double criteria. Example where the current is typically monitored. For example, this is now just one example with the relays and the point sensors. So the point sensors are typically monitoring, for example, in medium voltage, they are monitoring every closed compartment, which means that typically there is one sensor for the bus bar, one sensor for the circuit breaker, and one sensor for the cable termination, or any closed compartment. If it's a metal enclosed cubicles, metal enclosed switchgear, then you do not need to have a point sensor in each cubicle if the bus bar section is fully open. So one in every second compartment is fully fine, because if there's an arc flash in the bus bar compartment, it will travel hundreds of kilometers per hour to the end of the bus bar and through the wall. So current is typically monitored from the main incoming breaker, and that relay here is monitoring the current, and also it receives the light signal from any of the subunits or from the own sensors here. And the main thing for the relays here are to trip the main breaker, upstream breaker, and the tie breaker to isolate this left side if the fault is here on the left side. Then protection. What is different in detection and protection? For the protection, it is essential to first to ensure proper construction of the detection system. And for the detection, you need light, current, or light only, maybe pressure. But it has to be built properly. It has to be designed properly. So you detect the possible arc flash from each and every place inside the panel. So it can be very, very simplified with the fiber optics only, or it can be very or much more detailed with the point sensors and more locations. So ensure the proper construction is the key. Ensure that the necessary wirings has been properly done and tested. This testing is also essential. For the protection, you need more. You need to ensure that the good engineering methods has been used, protection philosophies Is it built like a very low cost system, or is it built like a all in with the best available technologies? Ensure that the correct main components selection and the condition, priority in CTs, VTs, circuit breakers. And simulate the faults. Test detection from every sensor. That is essential. Test detection from every sensor, but do not test the circuit breaker from every sensor. Because of, let's say that the big project has, for example, 120 or 200 sensors. You don't want to trip the circuit breaker 200 times. It's not really necessary, and it's not the circuit breaker should be tripped probably one time from each relay, but not from each sensor. It's essential that the circuit breaker will be tested and left also to a very good condition that is able to make the protection. We don't want to challenge the breaker too much. Another application example here. So this is a arc protection. This is called feeder selective protection. Again, different protection philosophies. Feeder selective means that if we have cable fault, for example, this feeder here, we only trip this breaker. And if the arc flash is here on the breaker or in the bus bar, then the trip goes to the upstream. And of course, that can be sent to another relays. For example, single line diagrams on the relay itself, and communicated up to the higher systems, for example, SCADA systems or any automation system. Feeder selective. Then the third step would be arc mitigation. This is something that what Emad and David mentioned earlier on already is the duration of the fault, arc calculations, calories. They mentioned these words quite a few times, and arc mitigation is probably something that there is a certain amount of magnitude of the fault always, which is very, very difficult to limit unless you do the design completely. You can change the protection settings on the relays. That is one way to do it, but it probably helps in some cases, and it helps. But the real magnitude levels, what we are talking about when there's a high risk with arc flash, are something which cannot be really reduced much with the settings. So these are some things like these PPE levels. What was shown there in presentations, that there was categories 1, 2, 3, 4, and some categories even higher than that, but they go up to 40 calories. But there are so many sites available where the calories go to 600 to 700. So it is not really easy to reduce that kind of level. But that's a little bit sidetrack, which I do often, sorry. But arc mitigation is something that it is very difficult to reduce the magnitude of the current, but it is easier to reduce the time of the duration of the fault. An incident energy calculation simplified to very, very simple mode is the magnitude times the duration and the square here. It's the total energy. So if we cannot press the magnitude of the fault, we can press smaller, the duration of the fault, which means that the incident energy square here will be significantly lower. So I'm just introducing ways to do that. Mentioned earlier already, arc quenching devices. There are different technologies. Arc quenching device is something which makes a parallel path for the fault current to travel. In the standards, it is said arc transfer current, arc transfer. So from the arc fault, which can be something which is a changing impedance, when arc electrode is burning, there is a changing impedance, and then it transfer something which is controlled. Very, very low impedance, but it's controlled. It's more like a star point to the system. So these units, arc quenching units, no matter what brand, their main purpose is to absorb the energy. As long as the main breaker, maybe tie breaker, and upstream breaker if necessary, they all open. Let's say the breakers which are surrounding the fault. So arc quenching device main task is to act fast, typically less than 5 milliseconds, always can be even 3 milliseconds. So now if you consider something that, for example, if you have 400 milliseconds trip time or 4 milliseconds total clearing time, of course it is a significant difference with the arc incident energy. So these are available from low voltage to medium voltage, different brands, manufacturers, and the technology is actually not new. For many people, they have never heard about it, but actually this technology has been introduced already easily 20 years ago. Here's some installation example. This is a medium voltage one. So it is wired and it is bolted to the main bus bars. And commissioning is recommended to do every 5 years. And not all of them can be commissioned. So there are differences, but there are some units which can be commissioned, and they are always the ones which can be reused. But if possible to commission, then it's every 5 years or during the maintenance program what your site already have. So if your site maintenance program and recommissioning program is 3 years, then you should use that. This is an example of the low voltage panel, low voltage switchgear, low voltage MCC or similar. There are many ways to say it, and different depending which part of the world you are, but low voltage port anyway. And very typical, the most typical low voltage port what you can find, it's called main tie main. So one of the main breaker is here, then tie breaker, and then another bus which is called main 2. And different relays, measuring current, measuring light, monitoring current, monitoring light. Same here, it's kind of a subunit for this, only monitoring light. And then arc quenching system bolted to the bus bar. And why we have 2? Because of the tie breaker. So if the tie breaker is open, we have a safe less than 4 millisecond system on the left side and also on the right side. So this is an example. If there's a flash anywhere in the board, relay will measure the current. One of the relays will measure or monitor the light, and then the quencher is closed and the breakers are opened. During the years, a lot of testing has been done for the products. This is also very high priority how I see it, it's a very high priority. If something wants to be proven or has to be proven or it's essential to be proven, only way is to test and verify. Another thing is, of course, to have a lot of installations and real activities on site or real arc flash incidents on site where this product works. That is also very good way, but the performance testing is clearly the most important thing when these kind of products goes into the market. Here is an example. Also earlier in some of the presentations, new standards were mentioned. Some part of the standards were mentioned. Typically, IEEE 1584 and 1584.1 has been used de facto standard. NFPA 70E also has been used de facto standard combined with this IEEE. And from NFPA 70E, you get the calorie ratings for the PPE levels, but there are a lot of other standards, global standard. IEC is seen very often like a European standard, but it is actually international standard. 28th of April 2020, new technical specification was launched called 63107, which is the arc flash protection and the mitigation system integration standard. There are a lot of IEC standard how do you build the low voltage gear. For example, 61439, 1 and 2. There are standards. How do you build the passive protection? We can say passive protection when it's like a mechanical protection. There are testing requirements after TR 61641 that who says that the doors should be stayed closed during the arc flash and after the arc flash. No cotton fabrics in 30 centimeters front of the panel should be ignited, for example. And there are new standards 6094791 and 92, which are released very recently. And these are then copied also to the BSEN standards from a Senelec point of view. So a lot of new standards. Also in Germany, DGUV has a new standard, and in Italy there is something very active with this. So IEC is actually getting, even IEEE is the de facto standard. IEC is working a lot, and these standards are getting very mature already, because the committees has been building these standards already long time. IEEE 1584 new standard, which was released 2018, was actually very well done, and it was properly done. They built it 16 years. They did more than 1,200 arc flash tests to actually prove the energies and the calories for a different horizontal or vertical arc flashes. So they have been doing also very good work with the standards, and very much hoping that the knowledge of this great work is also shared and understood. Here is one of the tests. This is the smallest power test we have done, and this is simulating the typical feeder protection. So let me run it. So imagine you saw quite a flash from here, but actually this test was a pass from the 61641 point of view. So the doors stayed closed, and it was actually a pass. So, but it looks very dramatical. We did another test again, this is related to the arc detection, protection, and mitigation. So we can consider this left side here to be the detection part. So we detect something with the sensors, but we don't trip with arc protection. It is tripped by the feeder protection. Or we protect with the middle one. We protect with the arc protection, and there is a certain 3 cycles circuit breaker delay. Or we can mitigate. We can reduce the arc incident energy by arc quenching device. So in the right-hand side, we mitigate by detecting, by protecting, and by mitigating with arc quenching device. And in this particular test, it was less than 5 milliseconds. So, and these videos here are fully synchronized, fully identical current, fully identical voltage, a fully synchronized videos with the high-speed camera, 1000 frames per second. And please concentrate to the right-hand side, bottom right corner, because it's quite fast video. So this gives a quite good, I think that the videos tells they are very self-explanatory when you have a look on these, that how the system actually behaves, how it works, and what is the difference with detection, protection, and mitigation. And it is quite a massive difference. I can also tell it from these oscillographs what is the difference. So again, this is now 30 kiloamps. So this is the smallest power test we did, 30 kiloamps, which is practically nothing today. It is a big amount of current, yes, but today the trend seems to be that the 30 kiloamps is nothing anymore. So the typical current levels are getting closer to 50, 65, 80, and 100. And the biggest current levels I have seen in LV boards has been 300 kiloamps. So the trend is there because of the lot of drive panels, microgrids, capacitors, big capacitance, or huge capacitors in the bus bars, DC network, DC grid, and it is getting these low voltage panels closer, already easily 100 kiloamps, but even higher. So in this one, this is 30 kiloamps, and this line here, it is how the power is seen, how the arc flash is seen from the transformer point of view. So this is the total power from the transformer, and the arc flash is definitely, it's horrible looking. It's very much distortion, and arc flash is something because it is not symmetrical in any way. The electrode is burning when you have high peaks from 3 phases. It is different. It changes in every cycle hundreds of times because the transformer don't actually know what it has to do. So it is just burning the electrode like welding. You have to move the electrode to keep the welding ongoing. So this is the total energy then for the arc flash. So actually the arc flash is already detected here. It can be detected easily in microseconds. That is not very difficult to build. But to react for that, we need to trip the breaker, and also that can be done very quickly. But then the circuit breaker has to open. And when you open the breaker, that is also an arc flash. When you open the breaker, you have another arc flash, which is parallel to this one. So now we have about 60 milliseconds here, arc flash, until everything is safe. And this one is the arc fencing device. So this is now the mitigation part of it. But notice this, please notice this, that this is actually more than half of the current, more than half of the power. And this is the difference. Now the arc flash is also seen here, and the arc fencing closes here. Already here, the arc flash from the fault perspective has been distinguished completely. So everything is safe. People or the panel or the process is safe. So this is that has been done. And now we have these 3 cycles. So the energy goes to the arc fencer here. And what is this peak? Like I mentioned earlier, is that when you open the circuit breaker, you will have another arc flash. And this is how it actually looks when you open the breaker. You will burn an arc inside the circuit breaker until that is completely cleared. And now we can compare this. It is a 300 kilowatts arc flash energy. 300 kilowatts. 65 kiloamps with the feeder protection. So this is how it looks when we keep burning the fault. So it carries on and on and on and on and on until it's cleared. And this arc flash burning here is about 5 megawatts. Of course, like you saw the first test with 30 kiloamps, we actually lost most of the copper from the panel. From inside the panel, we lost most of the copper. It vaporized completely already with 30 kiloamps. So this is 65. So when you see changes here, actually the coppers are practically already gone. And the explosion and arc flash keeps going until you lost the energy to feed the fault. And then we can also do the comparison with the arc fencing left side and without the arc fencing on right side. So it is a significant difference what comes to the incident energy ratings. 300 kilowatts versus 5 megawatts. And then let me try this one. Yeah, let's run it again. So this is 65 kiloamps. All right. Okay, so that was 65 kiloamps. So it was the left side from here. And it means that we wrote a white paper about safety beyond the standards, because our standards only mention about that every door should be stayed closed. And every country where I visit, everybody says that we never work with the live equipment, and every country where I visit, they do. So this is actually something incorrect, because when there is a way, when there is a will or way, how to say, these things happen. So people do work, they will do voltage measurement, they will do some test with the doors open, always in every country, even if somebody says that it's not possible, but it happens. And this is just a demonstration for that if the doors are open, what is the possible consequence of that. So yeah, I don't know if you did hear the sound also, but if not, then the visuals should show it anyway. So it looked quite nice actually that there was a spark only, but the coppers were. We actually have that panel still in our warehouse and we can use it for the next test. So I'm almost about to, if you want to see that video again, I will run it one more time, and then it's almost the last slide. So circuit breaker here, arc fencing device here, fault occurs on the right-hand side, and then we close the fencing device. And here's something which is coming soon, all about the arc flash conference. Something with standard regulation legislation, risk assessment, energy level calculations, partial discharge monitoring, and active arc flash protection mitigation and PPE. And something also to, a lot of people ask that how about the retrofit? Is it possible to retrofit these to old gear? That is actually even more done than the new build installations. New build installation, of course, everything new build is practically a standard already here. That every low voltage panel here in Finland, for example, and every medium voltage do have arc flash protection as a standard. But the retrofit installation, it is actually very big. For example, if you have 40 years old switchgear and you do the good maintenance for the circuit breakers, it is a good addition to add more safety, more like a additional safety on the equipment. And yeah, thank you for listening, and